Welcome to this video. In this video we will be talking about linear least squares regression and its application to some nonlinear functions. So by the end of this video you will be able to use linear least squares regression to fit nonlinear functions to data sets. What we've seen in a prior video is that linear least squares regression works with linear functions only. But many engineering problems actually are best described by nonlinear functions. So here's an example from the book of the measured voltage across a resistor as a function of time. And you see here on the left-hand side that measured voltage as a function of time has these blue symbols. And you'll see that a linear function will not be able to fit this data very well, and a nonlinear function much better describes the physical process that is described here. So the question is, can we rewrite nonlinear functions as linear functions? Because if we can do this, then we can use linear least squares regression to fit the linear version of the nonlinear function and then just transform the result back into the nonlinear form. So in general, that doesn't work, except for some very specific functions. Here's one example where this will work, a power function. So we have y is described by a model that is y equal to b times x to the power n. Now what I'm trying to do is I'm trying to convert this nonlinear function into a linear function. How do I do this? Well, let me take the logarithm of both sides of the equation. So I'm going to take the logarithm of y is equal to the logarithm of b times x to the power m. And now I'm going to use the properties of the logarithm on this right-hand side. That gives me m times the logarithm of x plus the logarithm of b, right? If you remember, if you take the product, or you take the logarithm of a product, that becomes the sum of the logarithms. And if you take the logarithm of something to a power, that becomes that power times the logarithm of the variable. Okay, so now let me define, or look at this first. So you see that there's a logarithm of y equal to m times the logarithm of x plus some logarithm of b, where x and y are my data variables that I'm trying to fit. And you might be able to realize that this function that I've written there after applying the logarithm is linear, not in terms of y and x, but in terms of the logarithm of y and the logarithm of x. To make this more apparent, let me define a new variable uppercase y that is the logarithm of lowercase y. And let me define an uppercase variable x that is the logarithm of the lowercase variable x. And then I'm going to just call a1, I'm going to call this m, or m equal to a1. And I'm going to call the logarithm of b, I'm going to call this a0. So let's substitute this in. So I get uppercase y, it's the logarithm of lowercase y. Uppercase y is equal to m is a1 times the logarithm of x, but I called this uppercase x, so a1 times uppercase x, plus the logarithm of b, but I called that a0. So you see here I have uppercase y is equal to a1 times uppercase x plus a0. That's our linear function that we fit using linear least squares regression. So we can then do linear least squares regression on this to find a0 and a1 using the logarithmic transform of my data pairs little x and little y. So once I have found the a0 and a1 by linear least squares regression, then the m from the original power function is just equal to my a1. And the b in my original power function is just e to the power a0. Okay, note, this minimizes now, with linear least squares regression, the error in terms of the uppercase variable y, because I'm applying linear least squares regression, minimizing the error on the linear form. This does not necessarily, however, minimize the error in terms of the originally measured value lowercase y. It's just a little caveat on this. Now, this approach works for other functions other than just the power function. And in the book, there is the table 6.2 that lists on the first column here the nonlinear functions where this coordinate transformation approach can be applied. Now, which one of these functions should you choose? Well, for many problems, there is a guiding theory of the physical phenomena that you're trying to calculate. And that determines then the form of the function. If you don't have that guiding physical understanding for the process that you're trying to fit, then this table here lists in the last column an approach to try to figure out which one of these nonlinear functions would best fit your data. And what it means is basically you plot the variables according to that last column here of this table against each other, and then you look at the resulting plot of your data, of your transformed data points, and see whether they kind of line up on a line, more or less. And if that's the case, then that would be an appropriate fit to your original data using the transformation that you just applied. There are a couple of other limitations when using these type of nonlinear functions. The first one is exponential functions cannot pass through the origin. So if your data goes through the origin, then an exponential functions might not be the right function to use. Exponential functions can only fit data that are either all positive or all negative y values. Logarithmic functions cannot include x equal to 0 or negative x values. And power functions require that the y value is equal to 0 whenever x is equal to 0. And finally, reciprocal functions cannot include y equal to 0. So those are some limitations that you can look at your data to exclude some of these nonlinear fit functions. But other than that, if you don't have a guiding physical theory behind it that dictates what the functional form should be, then you would do this process of plotting the data against each other and seeing whether that would be approximately linear. Thank you for watching.